Here we have an example of the electric field from a continuous charge distribution. We have an insulating rod uniformly charged with length 12 centimeters that's been bent around into the shape of a semicircle. The total charge on the rod is negative 6.5 microcoulombs. Wants us to find the magnitude and direction of the electric field at the center of the semicircle, or that is the center of the circle that the semicircle itself is part of. That sounds a little bit confusing to me. Let's see what we have. We have the rod, 12 centimeters long, has been bent into this semicircular shape. Let's put it on a coordinate system, and we're going to find the electric field at this central point, or that's the center of what the complete circle would be. It's going to show up again in a little bit. Might as well go ahead and mention that if the length of the semicircle here is 12 centimeters, then the circumference of the complete circle will be 24 centimeters. The circumference is going to show up. Let's pick a sample of charge, and we're actually going to integrate, imagining this sample goes from, thinking in terms of the angle, goes from pi and all the way around to 2 pi. But first we need to figure out the little bit of electric charge due to this sample. The length of the sample is dl. The amount of charge that it contains is dq. The electric field that it's creating, that small bit of electric field, is located at our central point of interest. We're going to need the vector that goes from the charge to that point of interest, call it r. It'll also be convenient in looking at this mathematically to imagine this r has been shifted to the first quadrant. So here is the shifted vector, so we can take a look at that. We'll need the coordinates of this piece of charge. If we call those x and y, then it turns out that the r vector itself is going to have coordinates the negative of x and the negative of y. That looks a little bit strange, but for instance, x itself in this picture is a negative number. So then the negative of the x works out to be a positive number and is in agreement with this being in the first quadrant as drawn. Calculate that little bit of electric field due to this charge. It's going to be k, the Coulomb constant, times the amount of charge divided by the distance cubed, and then times that full vector r. The full vector r, we can replace it with its coordinates here in ij notation. That's going to be the negative of x times the I, and if you prefer, this is plus the negative of the y times the j. Here to here, we're doing several things. One, I've taken the negative or the subtraction, I've factored that out into a negative in front of the entire expression. The x and the y in polar coordinates, those will be r cosine theta and r sine theta, while the sine or the theta is not drawn in the picture. That's the rotation angle coming around from the positive x-axis, so the theta is all the way around to here. Once again, the theta is coming all the way around from the positive x-axis and around to this line segment. Also, the dq itself is going to be lambda, the charge distribution, times the r times the d theta. That's going to show up on the next slide, so it's a little bit of backward thinking, but I'll try to make that one clear in just a moment. Simplifying just a little bit, the r and the r cubed and the r in parentheses will all cancel down and leave us with just a single r in the denominator, and I believe the rest of this is just copied over. And then if we want the full electric field, we have to integrate over all of the charges, and in going from the left side of the semicircle and around to the right side, we can imagine that the angle theta is going from pi in radians all the way around to 2 pi in radians. So there are the endpoints showing up And putting this expression into the integral, the k, lambda, and the r are all constant with respect to the theta, so they've been pulled out front. And we'll come back and solve the integral in just a moment. Here, taking a close-up, I wanted to show that relationship with the r, d theta, and whatnot. So here's our little bit of charge. This length is dl. The amount of charge there is dq. And now, just couldn't really make this show up on the previous picture very well. Let's draw out a sector that corresponds to this small piece of arc length. That's the radius of the circle, so r makes sense. D theta, if that is the angle within this sector, the central angle, then the dl itself, that length, as long as you're using radians, is going to be r times d theta. And the amount of charge, well, if lambda is the charge distribution and it's constant, the dq is going to be the lambda times dl, but we can substitute in the dl is r d theta. That's going to give the dq is lambda r times d theta. That was the expression that appeared on the previous slide. Miscellaneous, looking ahead. Having already worked the problem and kind of knowing what I'll need, I'm going to go ahead and sneak this in. So here too, a little bit out of order. The charge distribution, being constant, can be found from the total charge divided by the length of that rod. But the length of the rod is half of the circumference of the complete circle. So the charge distribution, rewriting a little bit, really is going to be double the charge divided by the circumference of the circle. Circumference of the circle is 2 pi r, but we can take that and solve for the r. That'll be the circumference divided by 2 pi. Or, if we remember in our expression, we're going to see it again in just a moment, it has the lambda over r. Well, substituting in, we have the 2q over c divided by the c divided by 2 pi, and that simplifies to be 4 pi q over the circumference squared. We know the amount of charge on the rod, that's given in the problem, and the circumference of the circle we said is going to be 24 centimeters, although probably want to convert that to meters at some point. Now let's grab that equation that we were going to solve, and fortunately this is a simple one. Working in polar coordinates, really just have to integrate cosine of theta and the sine of theta. Integral of the cosine theta is just the sine of theta. Integral of the sine of theta is the negative of the cosine of theta. So we've done the integral, and now we're going to evaluate it from pi to 2 pi. Substituting in, putting in the 2 pi, and rearranging. So a couple of things going on here. I put in the 2 pi, but ultimately it's going to be subtracting by putting in the pi. So I have combined that so that the I terms are together. We have the sine of 2 pi minus the sine of pi, going with the I unit vector, and something similar going on with the cosine. The sine of 2 pi is 0. The sine of pi is 0, so the entire part of the I expression cancels out, or just becomes 0. No cancellation even required. And for the j component, cosine of 2 pi is 1. Cosine of pi is negative 1. So we really have 1 minus negative 1 that's showing up here. I have also taken the negative in front of the entire expression and canceled it with the negative or subtraction here. That's how this ends up being a positive. 1 minus negative 1 is 2, so this is 2k lambda over r times the j. But the lambda over r was the expression that we solved a minute ago. That's equal to the 4 pi q over c squared. And if we substitute in all of our values, this ends up being about negative 2.553 times 10 to the 7 newtons per coulomb in the j direction, or because it's negative, really the electric field vector is pointing down. Just as an afterthought, it may be that you don't want to work with the IJ notation. Sometimes it's useful, sometimes it just requires extra writing to pursue it that way. But I should point out that you can separate it out and think about the x component and what that would be, and do this integral, and think about the y component and what that would be. And it does turn out, in fact, if we went back to the original picture from symmetry arguments, we could have said that the x component of the electric field vector is just going to be 0. We didn't really have to solve it at all. Could have just written that down. But I wanted to show that in a case where the math isn't too difficult, that the EX really does equal 0 in this case, and the EY is as we found on the previous slide. Phew! Thank you very much.